Smart City monthly seminar. Today, the theme of today's meeting is big data. Big data is an important part of the smart city application. So before I introduce our speaker, I have a group of students I want to introduce. We had recently the national competition on big data, and then we have a first place winner. So then you can have 5 minutes. Why don't you introduce about your work?
So we actually work at the transportation engineering department of civil engineering department. So our lab has a unique name like urban mobility and network dynamics. So we just want to show you what we did in the competition, just for a glimpse what we actually do on a regular basis. So this is the name of our urban lab, and just we actually do develop data-driven methods to solve different problems of urban mobility and networks, and traffic congestion, emergency response, and disaster management sort of things. So our team members is our supervisor, Dr. Sanal Hassan, the lab director, and the rest of us is the students, and me myself is Mohammad Asnaf, and Kamal Roy and Rizal Mani sitting in the back. So it was just the part of the Informs was the regular conference type meeting, and we will focus on what we did in the Midwest Big Data Hackathon. The hackathon is a part of a NSF funded project to sort of bring together all sort of data sources to merge together so that we can share the data and apply in various sources, like federal government is working, different universities working, and different government and non-government organizations are also coming together to share the data. So this was took place in Omaha in last 30 September. So what they did, they give a set of data set to choose from, and we had like from 10 a.m. to 4 p.m. to work with the data set and come up with a unique idea to how to incorporate the weather and the safety impact with the transportation problems we face. So we chose the data set of capital bike share data set, and we incorporated with it weather variables, various weather variables like rainfall and the visibility, the temperature, and other things. And from there, we downloaded the crash data set. This is the first is the FDOT maintained or USDOT maintained data set where they kept the data of fatal crashes of bike, pedestrian, and also cars. So the method we applied, we first approached with the regression method. We incorporated all the environmental variables we have found to find the demand of the daily basis. And from then we found out the crashes, and when we plotted the clustering of the crashes based on the clustering, so we can find out which zone is most vulnerable. And from there we classified the number of fatal crashes, like 0 crashes, 1 to 2 fatal crashes, or more than 3 fatal crashes. So this is the general idea of the regression model, the demand based on the variables, temperature, visibility, and the table we show the parameters and their coefficients. From the coefficient value is actually show the significance of the variables, and from that we can say that all the variables are significant, with environmental variables to predict the demand. And this is a simple scatter plot to show the relation of different variables. And this is a simple time series plot of the demand. As you can see, the demand actually rises as time goes by from 2010 to 2016. And also there is seasonal variation. I think during the winter, the temperature is low and the bike share demand is low, and during the summer season, the temperature is high and the bike share is also high. Because from the previous figure, this is actually the temperature versus demand graph, positive correlation or something like that. And this is actually the interesting plot. As you can see, you can find out some red dots and the green dots. Red dots are actually we can see with the attraction zones. In the red dots, there are more bikes are sent back to the red zone, and the green dots where the renting is higher than the giving back. So we can say that red dots are the attraction zone, and the green dots are actually the production zones. And also in the right figure, you can see the clustering of the accidents, the most number of fatal crashes. As you can see, the attraction zones actually suffer more accident. Just simple visualization of the problem. And from there, we have applied like linear logistic regression, linear discriminant analysis, k-nearest neighbors, and decision tree, naive Bayes, and SVM techniques to cluster all the types of fatal crashes, like as we told before, 0 to 1 or greater than 2 or greater than 3 clusters. And finally, we just draw some conclusion that the weather variables have significant impact, and we told the judges that the cluster centers where should we start our improvement from, so we can have a gradual process to improve the safety. And for the future research, we should bicyclists don't involve in the fatal crashes with another bicyclist. Normally they involve with the fatal crashes with another car and something like that. So we should also keep in mind the driving behavior of the big cities, like not only, this was capital crashes from Washington DC, we should also see Chicago, New York, and something like that. And this is just a glimpse of what we do in our lab. We also are working on travel behavior of the tourists in Central Florida or Florida region. Also, my groupmate is working on disaster management and like the evacuation technique of the people and decision procedure. Also, another result of mine is working on like real-time traffic prediction. So this is like smart city and big data. It's come together. That's why our supervisor wanted to show this. And thank you.
Congratulations on your award, and also you are going to the DC?
Yeah, we actually went to DC. There was a big...
You went to DC?
Yeah.
Okay.
There's like Google, Amazon, all sorts of big organizations were there. And that's the main theme was to share the data so that we can transfer it to new something.
And this hackathon competition is with the City of Orlando,
yeah.
Right? So this is annual.
This is annual, yeah.
So
we'll continue that.
We have many students here, so then I think I encourage you to participate. I think we will have another hackathon competition. So if you're interested, let me know, so then I can link to the City of Orlando. Okay? Right, thank you.
Thank you.
And today, our speaker is Professor Soibelman. He's a chair and professor of civil and environmental engineering in University of Southern California. So he has very interesting research on big data and data analytics in civil engineering application. So I'm very excited to have him. So let's welcome our speaker.
Let's go light.
Yeah.
Is it better?
Yeah.
Okay, so first of all, thank you for inviting me. It's a pleasure to be here. I'm going to talk a little bit about, normally I give talks that are more in depth, an example and I go in depth, but Andrew asked me to go with breadth. So I'm going to basically follow my career as an academic and how things evolved, and I started in one area and ended up moving to other areas, but all related to people drowning on data. I got well known when people have too much data, they come to me, help me. So I love those types of problems. So, but let me introduce a little bit my university. We're always looking for good master's and PhD students, so you are all candidates to. I cannot brag about the weather because we have good weather. Normally when I go to the Northeast and the other areas, I brag about the weather, but you have as good weather as you guys, so it's not the same thing as going to a snowy area. It's a beautiful campus. It's in near downtown LA. It's a nice city to live and to be around. Big football team. It's an interesting, very interesting university that was founded in 1880. We have today around a little bit more than 40,000 students. We have $4.4 billion budget, this year reaching $1 billion in research. Very interesting faculty. We have now 5 Nobel Prize professors, a lot of people from academic of science. Just in the School of Engineering, 31 of our faculty are members of the National Academy of Engineering. Engineering began in 1905, and one of the first engineering departments was civil. That was in 1906. We have around 600, 700 students. We have today 26 tenure track professors, 5 professors of practice, and you have around 25 part-time lecturers teaching a lot of our masters, professional masters. We are not a traditional department. We are not divided in construction, transportation, structures. We divide ourselves by problems that you want to focus. So you have faculty working in sustainability issues, water quality, and we have disasters and extreme events, and people working a couple of complex systems. So when I do data research that goes to all those 4 different areas. How my research started? I have an interesting different career. I'm originally from Brazil, and I had a construction company for 10 years. I had a lot of people working for me, and I was very unhappy. Making money, but very unhappy. I had the feeling that that thing was dirty, dangerous, that I didn't know what I was doing. So I decided to stop and get a PhD and came to the US, went to MIT, got my PhD. I arrived there with a lot of experience in construction, ended up at MIT, and I don't think that my professors ever saw a brick in their lives. So I had the feeling that I knew much more construction than all my professors, so I ended up doing my PhD in computer science. They didn't have a lot to offer me in the civil engineering domain there. And then when I graduated, I got a job as a professor at the University of Illinois in Urbana-Champaign, and they hired me again back in construction. So it was the moment that I had to sit back and think, what can I do? I have a PhD in computer science, I had experience in construction, so how I merge those things. And that's when I started thinking about the problems that I always had within construction. I started very early in construction. I have what I call a very dysfunctional family. My mom she passed away, but she was an architect and an engineer. My dad an engineer. My 3 older sisters engineers, married to engineers. So a Sunday brunch in my family would be just talking about concrete bricks. We never talking about anything else within our family. And I started in construction basically before even high school. My father had a big office, had his big desk and a small desk. I would sit in that small desk. Every day after school I would go to sit next to him and to see what he was doing. And it was interesting. My first job as a construction manager was with my dad, still in high school. He gave me the task of doing estimate and schedule for a project. So I got the blueprint, start measuring things, start with the numbers, how long it's going to take. So if I know how long it's going to take, I would know how many bricklayers I would need, I would know how much material I would need, I'd have the unit cost for all those components. I would go to a very simple spreadsheet, multiply those things, I would have the duration, how long it would take to do the activity and how much it would cost. And those things are published in books like Ars Means, here in the US, in Brazil, TCPO, but you have those cost compositions that use, okay, to build a square feet of brick wall, you need 2 hours of bricklayers, you have those things that they are simple averages, right? So I get the numbers and I would present to my dad with 50 years or 45 years of experience. He would look at me and say, oh, get this number multiplied by 2. And my feeling was, where is this coming with this from? Okay, he said, oh no, it's going to be rainy. You see, this is going to be done in the middle of the rainy season. It's going to be rainy. You're not going to be able to deliver according to the average that you got from the books. It's going to take double. So multiply by 2. So I always wanted to prove him wrong. I would get my stopwatch. I would go to the construction site, measure things to prove him wrong. And he was right. Every time he was right. Very frustrating. But then I realized that for him to be right, he had to lose money for 30 years making mistakes. All those patterns of connecting, oh, it's going to be rainy, it's going to be bad, was basically a lot of data that he absorbed during 30 years by doing it the right way, the wrong way, and building patterns. And it's what we do with big data. You get the data and you build patterns. And my question is, do I need to make 30 years of mistakes and lose money for 30 years to learn? Or can he give me those patterns, or can I learn from data? So this is the moment that I realized I'm going to work with data because I think that data can teach us a lot and I can avoid making past mistakes and learn from others' past mistakes. So the idea is that you rely on past experience to be able to perform our tasks. And I started asking the question, can I build knowledge base from previous projects? And that was the time, many, many years ago, when I started as an academic, that we started to have a lot of data. People started learning how to use spreadsheets, people were gathering data, there was the first databases, people are gathering data, but no one was using the data. And still today, much of the data that you acquired is not used. So the idea is that a construction facing explosive growth in capabilities to generate and collect data, but we are just drowning in the data. So this is what started motivating me to do my research. So one of my first research, this was in 1999. Yeah, this was 1998-99. This was a project from the U.S. Army Corps of Engineers in a city called Fort Wayne, Indiana. They were building this levee wall to protect the city from flooding. And they already had 3 phases done, and they were starting the 4th phase. And they had a lot of data. They had a database that was called the Resident Management System, the U.S. Army, RMS. And it had data irrelevant, because they didn't know the data that they needed, but they were gathering everything. I say that they had the color of the underwear for workers. They had everything, everything. You look at the data and say, oh my God, I don't need the color of their underwear. But they had everything. And they were behind schedule. All the 3 phases, they were behind schedule. And they said, we are going to start the 4th phase. Can you learn from the data? So it's a repetitive task. They're doing it over. Come on. They're building a concrete wall. I'm not talking a complex thing. They are building a wall, and then the wall again, and then the wall again. They go for miles building the same wall. Okay? Can't you learn and do it right once in your life? No, they had mistakes over and over again. And they didn't even know why they were behind schedule. So I went there to the construction site with my student. His name was Hyunju Kim. He's a professor in the University of Seoul. And I went with Hyunju. They had trailers. And to build wall, they had 7 engineers, managers. Okay? Come on. And none of them had a clue what they were doing. Okay? And I asked, why you guys are behind schedule? What do you think that they answered me?
Workers?
Hmm?
Did they say, I don't know?
No. The engineers always have an answer. They don't tell you. They always know. They know it's wrong, but they know. Okay? What do you think that was their answer? Come on, anyone ever worked on the construction site here?
Material delays?
No, material delays people avoid saying because it's your fault. Okay?
Weather?
Yes, it's God. Okay? When you say, oh, weather, I can't control that thing, but materials delays, it's your fault. You didn't buy the materials when you should. So everything else that you'd say that you are behind schedule, oh, there are not workers. Why didn't you hire the workers? You are the manager. Oh, the materials was not here. Why didn't you bring it the right time for it to arrive? You didn't consider the time that takes for delivery and those things. So everything else would be their own fault. Weather, it's the excuse that they always use. It's God. I cannot control. It happens. So you went, and it was funny because this is 1999. Okay, they had a computer connected by telephone. I don't know if you guys remember those things, those telephone modems. They were connected to a thing that was pretty new. The first browser was built in 1993. So this is 6 years after they invented the browser. Okay? There was a brand new site called weather.com. So I went to that site and I typed the dates of their projects. And from 1995 to 1999 were the driest years ever in the history of Fort Wayne, Indiana. And I said, guys, weather, data is telling me that it's dry. I believe in data, okay? You trust God, I in data, okay? But I was talking to them and said, look, cannot be the weather. And then they don't give up very, very easy. Said, no, you're looking at aggregated. Our problem is that the weather was bad when it shouldn't. Okay, every time that you excavate to do the foundation, you'd have rain, by coincidence, happened in those days. And then you had cave-ins, you had all those problems, and you have to pump water out. So it rained not a lot, but at the wrong time. Say, okay, so let's look at that. The data is going to tell us that. So I start looking and crunching the data, and it was funny to see that weather had no impact at all. Okay, their main problem just from the data that they had. Okay? Their main problem was we found out using decision trees, C4.5. We saw that he used CART. It's the same algorithm in the back. It came with inaccurate site survey. That meant that there was boulders. Okay? Those guys start excavating. Ooh, a big, huge piece of rock, a boulder. Oh my God, I have to remove the thing. Second reason for delay, lack of equipment. Oh, I need a big equipment to remove the boulder. I don't have it. So let's wait for 2 weeks for the equipment. Okay? Shortage of equipment. So basically, weather would come as season. And the third layer of the reason for delays, but because they would start on month 5, and they should finish before winter, but because they would have delays during the process of doing those excavations and everything by encountering those boulders, the project would move into winter, and then the weather would affect. But would affect because they were incompetent in the first place not to finish the project before winter. So what we did, we told them, very simple with the information, told them, buy this piece of equipment. This is a GPR, ground penetrating radar. Okay? You move the thing, and it creates a map of the underground. You find the boulders. So I said, you get this equipment 6 months ahead of the construction crew. Okay? You map the underground. You find boulders. Now you have 6 months to plan for your equipment, to get the equipment, remove the boulder, but you have to make sure when the construction crew arrives at that point, you are not going to have boulders. And then you are going to deliver on time. And indeed, they delivered on time, and for this equipment that costed at that time cost $5,700, they saved more than $1.5 million. And they delivered on time with their own data. So you learn that, yeah, there is a potential. By using the data, there is a huge potential. You can learn from your own mistakes. Problem is that the quality of the data. We indeed had the color of the underwear. How I remove the garbage, how I clean the data, how I prepare the data. So all our the lessons learned from this specific project, it's almost irrelevant to the next project. So what we had to create is a framework, a step-by-step, that would let people crunch their own data. How do you do? And 80% of the effort was in data cleaning because you are so incompetent that you don't even know how to acquire the data. So after this research, then I really love to do research when people come to me with problems. I don't start, oh, I'm a data guy, I'm going to use neural networks in every type of problem, like a kid with a hammer that everything looks like a nail. Said, what are the problems that you have? So this was, I got people start saying, oh, you are drowning on data, let's go talk to Lucio, I think that he can help us. So this was a company that was an extranet provider. Extranet providers that when they invented that website would be interesting for construction projects. You have architects, project managers, structural engineers, you have a team of people that got together to design and build a building. And each one have the files, different files, that are before were kept in paper in their office. So if I would be working as a structural engineer and I need, before I would need the detail for the roof, I would call the architect would make a copy of the blueprint in paper and would send someone or mail it to my office, and then I would work and do my work. Then people start exchanging as emails, and there was a moment that everyone would upload to this central repository that you go and you search and you retrieve each other's document. The problem is that projects started to generate too much documents. Text documents, for example, was a huge bottleneck. An average project was generating 1 million pieces of text documents. Change orders, requests for information, specifications, contract, all these are text, emails. So let's see that. I am an engineer building this building, and I have a 3D model with this wall, and I want to build the wall, and the specification is the wall that should be white, and the client send email to the architect saying, I hate white, paint it black. So how you find that piece of email if you have 1 million documents? And then what happens is that in the real world, I would, as a construction manager, not find the information, would build, paint it white, and the owner would come here. I send an email to the architect, it should be black. What happened? Oh, I didn't get access to that information. So this was the daily operation. So I said, we really need to organize those files in a way that people find the information that they are looking for. Kind of a search engine or something. So what I decided, this was Carlos Caldas, a PhD student, he's a professor at Texas Austin now. And what I challenged Carlos to do is said, Carlos, do a kind of a classification, classify all the documents according to construction objects, and then you can go to a 3D model, what you call a BIM, a building information model. I can go with my mouse in the 3D model, I click in the virtual wall in the model, and I retrieve every text document. So the email would come, the email from the client saying that wanted black, the specification, the change orders, everything related to that wall would be linked to the wall. So the problem is that how you classify, how you associate, and how you retrieve those documents. If you think about Google as a search engine, Google has, the only thing that Google has is retrieval and ranking. Okay? So when you do a search for my name, Soibelman, okay, they do, for example, when you do a research for USC, Civil Environmental Engineering Department, okay, comes the page of the Civil Environmental Engineering Department, doesn't come my page. But my page talk, chair of the Civil Environmental Engineering Department. Both pages have the same text. If you would be looking for the document that has that term, Civil Environmental Engineering Department, both would be the same relevance. Why that department is more relevant? Because Google uses number of hits. So that page is seen much more times every day than my page. So I said that page should be more important. And number of links. My page is my PhD students say, I work with Professor Soibelman, but the department page, every student make a link. I am a student of that department. Every professor, I'm a professor in that department. So there are millions of links to that page, and my page has 5 links. So Google infers that that page is more important and rank that on top. Construction documents don't have links and don't have hits. And even if it doesn't have hits, if the email asking me to paint is black was seen by anyone, I want to see it. Okay? I don't care if it's not seen. It's important for me. So you had to find a different way to solve this problem. Carlos, and this is interesting, when you're solving those problems, we have to go outside engineering. So Carlos took all his classes in the School of Library. So they are thinking about how to organize text documents. So it's where you have to go and take your classes. You have to go outside your domain and fix the problem. So he went to a theory that's called information retrieval, and he organized all the documents into this vector representation. So you have, for example, 1 million documents, so you're going to have 1 million columns in this vector. And then the rows are the terms, the vocabulary of words in construction. Okay? So you have 20,000 around in English of terms for the construction vocabulary. So you create this matrix with 20,000 by 1 million. For example, we had a project, we validated with 20 different projects. We had a project that the architect was in England and the project manager was in the US. So the architect would talk about the lift and the project manager would talk about the elevator. So even the term, if I do a search for lift, I would retrieve all the documents that were generated in England. None that the documents talking about the elevator generated by the engineer. So again, you need to have an ontology, you have to have a representation, a synonym system in the back. This is not feasible. Okay, people are trying this. This is the holy grail in information retrieval, okay? To create those ontologies that represent everything. So you need to find a better way. The solution here, so if you have the document, so basically you have, think about the elevator. You have the term lift, yes, 1, no, 0. You have the term cable, yes, 1, no, 0. You have the term shaft, 1, yes, 0. So the numbers here are not 1 and 0 because you have the frequencies. But again, think about a binary representation. So you have the word concrete, no, so it's a 0. So if you have a document that has 20 words, so you have 20, you have a matrix with 20 ones, and the other 9, because if it's 20,000 words, the other 19,980 are zeros. So it's a very sparse matrix. If you remember from high school, sparse matrices are very easy to deal with, okay? Very easy to represent mathematically. So you know you can represent documents as vectors, okay? Those ones and zeros. Okay? So you can imagine that when you're doing a search for the document talking about the lift, you retrieve every document talking about the elevator, because even if you don't have the query word, you have other dimensions that are very similar, because you're going to have shaft, cable, stops, things that are relevant to documents that talk about elevator, and it's going to make those two documents very near each other in this vector space. And then it's basically how you solve it. So you go from a B model. So we start with IFC, and then you go, for example, you have a model of a building. You select, in this case, an element, an object, of electric fixture here, and then you do a search, and then comes every document that talks about this specific element. And here in the parentheses, the distance from the query vector to the document. So you can calibrate. Okay, you can bring more documents by increasing this distance. Probably going to bring more garbage together. Or you can augment, so you can calibrate what you call recall and precision. So basically it worked extremely well. We did 20 validations. So what I said, recall and precision. Recall is that if I have 10 documents talking about Lucius Soibelman out in the internet, and the search engine finds 5, okay, so I have a 50% recall. It missed 5. Precision is that if I bring 10 documents about Lucy, like 8 are talking about Lucy and 2 are talking about something else. So came 2 documents by mistake. So we say that I had an 80% precision. So as I said before, with this approach you can calibrate recall and precision by increasing the distance of those vectors. You increase the recall, but you decrease the precision. But again, for us, recall was more important. I don't care if I bring a document that don't talk about this wall, but I don't want to miss that email talking that I want the black wall. And because I just have 1 million documents, not like Google that has trillions of documents out there. They are very concerned with precision, okay? I'm very concerned with recall. So it's not really fair to compare, but here there is a comparison. We went almost to 70% recall. That was the most important thing for us. So system 1, it's Google, the Google algorithm, about 42% recall. Project manager was Bussoff from Autodesk at 44. So there was a huge improvement in recall. And even if precision wasn't the most important thing for us, we still got a high precision. We got around 50% compared to Google that's 30%. So you retrieve 70% of the documents that talk about the wall, but 50% of the documents that you bring are not relevant to the wall, but I can sift and get rid of them. Then a construction company came to me and said, look, W. O'Neill, we love your research on text documents. Our problems are pictures. You are drowning on pictures. People are taking pictures with, this was even before cellular phone, but everyone had those digital cameras taking pictures. Name of the pictures, MVV123.jpg. Okay? So you have millions of pictures in a project. So let's say that after 2 years you have a crack in this column, and you as someone that wants to know your liability, you say, do I have any picture of that column during the construction phase? So how am I going to search in 500,000 pictures that are called MVV123.jpg? I have to open one by one. Okay? Or even worse, this company labeled extremely well their pictures. Okay? The name of this picture is domestic water mains.jpg. It's this copper pipe here, the reason that they took the picture. But then when you realize that, you say, oh my God, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. You have several objects in this picture that are there, even if you took the picture. So if I have a problem in this column and I want to look at the pictures, I'm not going to look at the picture called domestic water mains for that column. So I got what we call an undergraduate research opportunity in the summer. I got undergrad students I gave them thousands of pictures and asked them to count how many objects you have in average in a construction picture. I made sure that those students are never going to be researchers. Those are the ones that for sure are going to industry. So they counted. If I can trust them, if they didn't lie to me, they got a mean of 45 objects per picture. From 0 to 300 objects in the picture. 0, it's that one that someone takes a picture of their own foot by accident and put in the database. Okay, no construction object at all. But 300, it's 300 things. So can you imagine if I want to name those pictures, I would have to give the name of this picture like this. Still column 13, still column 22, still beam 09, still beam 10. I would have to go for every picture and give 45 names to it. Who is going to do that? Either we automate this process, or those pictures are irrelevant for us. So this was a challenge. I love to challenge my students. Then I walk away. I find the problem. Then I say, okay, have fun. So this was Yanis Brilakis. He's a professor at Cambridge in UK. So he did he went outside, like Carlos went to the information retrieval, that is the Library of Information Sciences. Yanis had to go to computer vision, had to go to robotics, and to learn. So what he did a representation of pixels, the clustering, recognized all the objects, extracted objects, because those pixels are different than those pixels that are different than those pixels. You can do using clustering and separate objects, and then he used signatures of texture to find the materials, and then if it's linear, he can know that it's a column or a beam. If it's flat, he knows it's a wall. He used information about when the picture was taken, because you have something called 4D, that's the schedule. Every object knows when it was built. So if I'm looking for a column that was built in October, every picture taken before October cannot show that object. So you can eliminate and reduce your search space. Use the position, indoor positioning system in the camera, so everything that's behind the camera cannot be. So we did a search by reducing the search space. And again, so Yanis was capable of going to an object and say, find me all pictures that show this wall, and then he would retrieve. He got 100% recall with 50% precision. So all the pictures that show, we did again the validation, in this case with 35 projects. We tested with several different objects, and basically you bring all the pictures, but you bring a lot of garbage too. That's okay. That's a way that you have to improve. So then, it's when I got my second job. It's when I moved from Illinois to be a professor at Carnegie Mellon University. Carnegie Mellon started with a program called Advanced Infrastructure Systems. So they started thinking about smart infrastructure for cities, big cities, not just in cities, but infrastructure at all. So thinking that your car tells you when the door is not closed, you see a light. Some cars even tell you which door it's not closed. Okay? Tells you when your tires have not the right pressure. New cars even tell you which tire. Tells when your oil is low. Tells when the water is boiling. Okay, it's hot. The engine is hot. So your car tells you a lot of things. Okay? Think about a bridge. Okay? A bridge collapses and kills people, and the bridge doesn't tell you. There is no information about, hey, I have a problem, close me. Or I have a problem, reduce the number of trucks that are allowed to drive per hour here. Reduce the maximum load. So the bridge could behave like a car. You could have a much smarter bridge. and it's not. My car has more sensors than the whole transportation network, all the bridges in the United States, I think. Okay, so that's something that it's really crazy. Compare the value of a car and compare the value of infrastructure, and we don't talk a lot about that. So the idea behind is that we have to move information communication technology to sensor-based and smarter infrastructure. So this was the group that they were creating. The problem that they were facing was that they were very good in electrical engineering, they were very good in computer science, they were very good in those areas, but then they start putting sensors on bridges. And sensors moves the problem of data, big data, in an exponential way. You have those sensors reporting 60 hertz, 60 measurements per second. So you have 200 sensors in a bridge. You are generating terabytes of data every day, and how you analyze the thing. And the analogy that I use is the human body. If I have pain on my knee, okay, it's not I have pain on my knee, stop. Okay? You have some reasoning. Oh, I have pain in my knee, it's a small pain, I'm going to get a little bit of ice. I'm not going to run now, I'm going to wait for 1 hour. Oh, it's a strong pain, I think that I should not run at all today. Oh, I think that I should go to a doctor. So you do a lot of reasoning with the information that's coming from the sensor that it's the pain. The same thing with the bridge. It's not a question of having a binary thing, there is something wrong with the bridge. Could be thermal stresses, could be things that are not relevant, that the bridge has no problem at all. But again, who makes this analysis? Who decides where the sensors? How many sensors do you need? You need to bring a lot of civil engineering, a lot of structural engineering understanding, a lot of data. So this is really an interdisciplinary area. And again, it's not, there are bridges that collapsed with sensors because the sensors were in the wrong place. Okay, they were monitoring bridge, the bridge was in trouble, they put the sensors, and the bridge collapsed. And they had the sensors and no one really saw it because, yeah, there were electrical engineers that had no understanding about the bridge. Okay? So and then I started doing research again, people coming to us. So this was a company called Zone Robotics. I'm going to have to run because I have just 15 minutes, but Zone Robotics send those robots down on sewer pipes, and they have cameras, okay, and they are trying to find defects on the pipe. So there is a guy driving this in a trailer, drive this robot, and here it's a map of the city. Those are all the pipes, okay, and those circles where this operator found a defect, stopped the robot, took pictures, and classified according to an ontology of defect that's called PACP. So you can have a defect, a structural defect, that's a crack, that's a spiral crack. So this person goes, okay, this is a spiral crack, structural spiral crack, classifies it, geocodes it, and gives. So what this company with this big robot that they call the responder, they would not sell the robot. They will sell these. They sell the service. They come to a city like Orlando, and they convince the mayor, I'm going to map your sewer network with all the problems, and I'm going to charge you $3 million, and I'm going to give you this map. With this map, you're going to see where the problems are, the diameter of this circle is how critical the problem is, and then the mayor and the director of the water resources, the water authority would go there and look, click at those circles and like, okay, I can see the defect, this is near a hospital, this is an area, so they would find a priority, what to fix first. Obviously they cannot fix everything, there is never budget to fix everything, but they would have a much better planning of what to fix first and what are their priorities. So everything done, this guy done, they have 3 of those robots, they are traveling the world, making millions of dollars, very profitable. But then they developed this one, the Solo. So this robot they don't sell, cost them $3 million to build. This robot, the Solo, they are selling it for $10,000. Okay? And this damn thing goes alone. Okay, a city like LA bought 30 of those. And they get in a pickup truck, put 30 of them, they go to manholes, drop them there early in the morning, and now they have 30 of those robots going to sewers around under LA. At noon, those guys come back, get those 30, clean it a little bit before lunch, okay? They clean it, they connect to, there is a USB port, they connect to their computer and they download. Okay? And in the end of the day, the guy with the pickup comes back to the office with 150 to 200 hours of videos of pipes. Okay? So now this guy that was in the trailer has to go to the office at night and watch 200 hours of video. You don't have 200 hours at the night. So if you're going to do at night in 10 hours, you need 20, 30 guys sitting for the whole night to look, to geocode, to classify. That's when they say, we're drowning in data. We cannot deal with this amount of data. We need to automate this process. So it's when they hired us to do the research. Again, we failed. Research fails. It's very difficult, a difficult problem, because if you think you could find the defect, but you could not classify it. A spiral crack is very similar to a circumferential crack. And I'll tell you, it's very dirty down there. Okay? There is a brown thing that smells bad, that's stuck in everything. Okay? And the lighting conditions and everything, it's not a very good algorithm. But one thing that we learned is that by watching hours and hours, at the beginning you would watch those videos and you say, in the end we'd have lunch meetings watching the videos. And the rats would be walking and everything else there. But the interesting thing that we found that we had long segments of healthy pipes and then a problem. And then again, long segments of healthy pipe and a problem. So I start measuring what is the percentage of healthy pipes with defective pipes. And in the worst network, that was Philadelphia, Philadelphia has a lot of things of worst, but that was, it's the oldest sewer pipe in the country. So they have wooden sewer pipes there. It's beautiful to see that. It's still there, working. But we look at those things and we realize, okay, but if there are so many segments that are no problems, why do you need to watch it? So we transformed our classification algorithm into a detection algorithm. And you say, okay, if I can detect and I can remove the 80% of the image, say, I know that there is no problem here, no one needs to watch this. And I would give them 20%, so if that 100 hours that it's arriving at LA office, I reduced to 20 hours. Now they with 2-3 guys, in place of 20 guys, they can do the same job. So it's a big gain. And indeed, that was very easy to do. Finding that there is a problem, it's easy. Telling what the problem is was more difficult. So we just did this detection algorithm. We are very happy. Popular Science consider our algorithm to be one of the 25 new technologies transforming Crumbly infrastructure. I'm going to run. I'm not going to discuss this one. This is a cool one. This is a systems of systems problem. We're looking at hurricane for the Department of Energy data and trying to understand the impact of energy production. Here is water too. I don't have time. I want to go to this one. How powerful data can be. So this is a work that I did with a student called Mario Burgess, and Mario is now a professor at Carnegie Mellon. So this was started from a curiosity in my own home. I had a huge electricity bill, and I went and replaced all the bulbs in my house. Oh, I cannot pay this bill, and replaced the bulbs. And the next month, the electricity bill came exactly the same as the previous month. I said, what did I do wrong? I changed all those 100 watts bulbs by 5 watts bulbs. Yes, I work 24 hours a day in the office. My house is dark, okay? If you replace 100 watts bulb by a 5 watts bulb, you save 95 watts per hour that you are using the bulb. If the house is dark, it doesn't make any difference. So I said, I have no clue why I'm spending all this. And I realized the analogy that I used with these children, I said, I would love to have an electricity bill that looks like a supermarket bill. that I would look at the supermarket. I spend $100 and I say I'm spending $30 in meat. It's 30% of my expenditures. No, I'm going to be vegetarian. I'm going to save 30%. I can make decisions and predict, or I'm going to change from red meat to chicken and probably can spend 15%. I don't know, but you can replace things for a target and have an objective. In electricity, I have no clue. I said, should I change the thermostat in my air conditioning? What should I do? What's the impact of everything? So I really would like to have an electricity bill. I spend $10 in lighting, $15 watching TV, $7 in air conditioning, and then change and do something. So I challenge, and this is a big problem. If you see, for the total energy production in the US, you talk about high efficiency cars and everything, but look, for the whole energy that you have in the United States, 40% of the whole energy consumption in the US is for electricity. And for this 73% of the electricity, it's used by buildings, not by industry. It's commercial and residential buildings. If you make buildings more efficient, you can have even bigger impact than making cars that are more efficient. Okay? So what I did with Mario, Mario went to my house, test, and there are some funny consequences. Went to my house and he developed the hardware and the software. So he developed a pass-through meter that you connect to the outlet, a big small box, you connect to the outlet, then you connect your refrigerator to that box. All the energy that comes through the wall passes through that box and goes to the refrigerator. That thing is measuring. And that thing has the small antenna, wireless, and so we had the computer that was getting all those sensors and measuring the refrigerator and everything. First thing that happened, I put the dashboard, the laptop with the control, with all the consumption of electricity in the kitchen, and I had an electric range at the time. So my wife stopped cooking. She realized it's too expensive. She always considered the price of the food, but not the price of cooking. She said it's cheaper to go to restaurants, so let's not cook anymore. So be careful with the research. and for sure, hide from your wife. Don't put the screen in the main entrance in your kitchen. But we were able to find the real reason, and you were able to save 30% of energy. My house was the pool and was the air conditioning. So by changing the thermostat a little bit and by cleaning the pool 3 hours a day, not 5 hours a day, I was able to save 30%. But I was informed and made my decisions and changed. The problem is that to develop the hardware, we spent $60,000. Yeah, $60,000, and my electricity bill was expensive, was $200, but 30% is $60 a month. So a $60 a month saving from a $60,000 investment, if you know a little bit of net present value of those things, you're going to realize that that's pretty stupid. So what I challenge Mario that we start looking, and it's a little bit difficult to see, but this is the coffee machine that we monitor the department at Carnegie Mellon too. So this is the coffee machine. This is time during the day, and this is watts. Okay, so you have here a spike. This is the water heater. Then you have here someone getting tea, someone getting coffee. So you realize, oh, every time that you do something, you have a spike in energy consumption. And this could be a signature of appliance. Can I recognize when the refrigerator goes on? If I can recognize, then I can track the energy of that appliance, and then I recognize again when it turns off. So this was pretty interesting because we realized that the staff that was taking care of the coffee machine was stealing money, because you could count how many coffees you were selling per day, and she was lying into the value. So we already saved money by firing the staff. So this was a very productive research. But again, so I said, if I can do that, if I have one sensor in the house, in the house with two phases, if I have two sensors, not the $60,000, 100 and something sensors that I put in my house, can I, with one sensor, track the all appliance energy consumption at home? And indeed we are able. So here you can see a stereo going on, a light bulb, you can recognize everything, and you indeed were able to create that electricity bill that looks like a supermarket bill. It was funded by Bosch. We got several patents. So it's a regressions and you go. So you can go in real time and you can have from this one sensor you can have this is air conditioning, this is lighting, this, and then you can divide in real time. So the idea is that in real time you can change your thermostat and you see the impact that you have in your energy in real time. And then you can start predicting by the end of the month how this is going to affect. So I thought that I was a millionaire. I'm going to sell, patent, everyone's going to buy this. So I deployed it in 50 houses. Deployed it in 50 houses, and I did a mistake that researchers shouldn't do it. Every time that you do a research, do it for 1 week and walk away. Prove that it works, don't leave it there, okay? So what happened is that we put in the house, the average saving in the 15 houses was $20, was 20%, okay? Very high. You can imagine every household in the US saving 20% energy. How many power plants you're not going to build in the grid? This is huge. The problem is that we left there for a longer period, and people, all of them went back to their old behavior after 2-3 weeks. Why? Energy is too cheap in the United States. An average house spends $60 in electricity a month. So 20% is $12. Now your beer is warm, your house is warmer. There is a trade-off. You can get savings by reducing your thermostat in your conditioning, reducing the time that you're cleaning your pool. Now your water is getting greenish. If you don't like green, if you prefer blue, it's not a good idea. So you start having those things that you can achieve your goal, but there is every trade-off on comfort and those goals. So you learn that the problem is not an engineering problem. So we've been working now for the last 5 years with colleagues in psychology. So you want to change behavior, so you have to find out how to present. So I have a PhD student, Simin, the one that I was telling. She is looking into wasteful behaviors by comparing the houses and finding out for people what to do with one another. So we keep working this one area, very active area of research. I'm collaborating with a colleague, Jean Besser. She's an expert in what we call human building interaction. So we are learning how to do those things. So basically, there is a lot to be done. If you have data, you can improve construction, operations, the whole life cycle of buildings and whole infrastructure systems. So that's what I had for today.
Thank you very much for the very interesting talk, and we have questions. We can have answer some questions from the audience.
No questions. That's good.
So I have a question about the model that you showed us from the parsing the document and those things. So how did you link it with construction drawing?
I don't know how much you know about BIM, Building Information Modeling. So building information modeling is a representation that allows every object to have a description. The idea of building information model is for interoperability of documents. So you have the documents coming from a structural engineer and the architect. They use different softwares. So you have this common language that represent all the objects that you know that the column in the architectural drawing is the same column in the structural.
Okay.
So, and this is a text representation.
So the document has some information.
Every object has a text description. The document is text, but in BIM, every object in construction, every column has what you call an industry foundation class, is the representation for the objects, using this common language for interoperability, and this is text.
Okay.
So by clicking at the object, you can extract from IFC a text description of the object, and this is how used for our query vector. So now you create the query vector, and now you see the documents that fit that query vector. So that is pretty easy. But because IFC exists. If not, you'd have to come with a description, text description for every object. Because it's text comparing text. And you didn't have for images. So this is why image you had to reduce the search space.
So on the work that had, where you're taking pictures and identifying elements, are we seeing that sort of get changed all over again with augmented reality now? The Google glasses type things, where you're projecting your design drawings over that?
It helps because if you, when you are working with those things, you really have to extract the object. So I keep working on that thing. I'm working a lot with 3D modeling. So I have a lot of work with drones today. I didn't have time to present. They're here. I went slow in the beginning. So laser scanner. So we're creating 3D models of buildings. So you're using the same principles for extract pixel information in the 3D models. I'm working for the US Army. What happened is that you can fly a drone around the building, take enough pictures and create the model of the building. The problem is that the precision that you get is at the centimeter level. Okay? You can do the same thing with a laser scanner and get the precision at the millimeter level. Okay? The main problem is that in an existing building, I can get the walls with the laser scanner, but those laser scanners are heavy and big and tripod. I cannot get the roof. Okay, I cannot fly the laser scanner. I'm flying now laser scanners that are getting this wall. But what we did in the past, we created hybrid models. You got laser scanner wherever I can get with the tripod, and then I fly a drone in the air that I cannot reach with the laser, and then I patch things together and I create a model that had precision that varies according to what tool was used to acquire the data. So now I'm able to drive some fly a small LiDAR on drones that doesn't create millions of points, but I can create a kind of tracing points to correct the photography. So I'm getting very high precision models.
So you're feeding that into your structure through motion algorithms, basically to improve the models that they're producing?
Yes,
Yeah.
but what happened, we got very high quality models, and who hired us to do now, it's the Army. Why the Army wants this? If you have a war in Fallujah, okay, that's happening, and you are going to send soldiers there, you want to know exactly where all the buildings are. If you know where is the sniper, you want to know the angle of view of the sniper. So if you have an error, if you have a sniper here and 2 buildings here, the angle keeps opening. Okay? If you have a 30 centimeters error here, when you're half mile away, you have meters of unknown areas if the sniper is seeing or not the shooter. So they really need the high precision to be able to guarantee the security and safety of the soldiers. And we are designing, it's a path, a transportation algorithm, the shortest path, but the shortest path overlapping with the areas that the soldiers should not walk because they could be shot by the sniper. And so now what we are doing, after we solve this problem, they realize that my previous research in extracting objects is extremely important because we have to extract windows. Okay? If a shooter, if the soldier is behind a window, okay, the shooter is going to shoot him. Okay, so the building is not all solid, so you have to extract the objects that are transparent that the shooter would be able. So you have to tell the soldiers, we're behind the building, but this is a window, glass window. They're still seeing you. Don't be that stupid to hide behind a window. So again, change the whole path if you know where the windows are. So you're doing automatic extraction of windows. And this has to be done in real time, so those soldiers are flying with, are carrying those drones in their backpacks.
Yeah, so that's what's interesting about this, because it's very, I mean, are your algorithms able to do that in real time? Do this, create the 3D models? Or are you working with existing models and adding on to it?
No, we're creating in real time. Yeah, but it's not just us. The Army has 20 people working in this. I have 2. Okay, it's a large group. Just to have an idea, if you use the DJI software, okay, because you cannot fly the drone in a war and have a view, okay, so you have to use waypoints, okay, so you have to tell the drone, and the drone has to fly autonomous. DJI has the autonomous waypoints of flying, but it's extremely slow. The drone flies at 2.5 miles per hour. The Army has an algorithm that the drones are flying now at 45 miles per hour and acquiring data. So we are able to do the whole USC campus. With DJI, it took us 30 days to do the data acquisition. With the Army new algorithm, we did in 25 minutes. Okay, those drones fly at a high speed, but it flies higher. So you have to do a lot of recognition. For example, when you get trees, you get just the top of the tree that's much bigger than the rest of the tree. Okay? So you have to do automatic recognition where is a tree to do a replacement, because the soldier can run under the tree. Okay, it's not the whole volume. So there is a lot of algorithms that you are developing for them, but they are amazing. So yeah, we have all those algorithms to create those things in real time. Pretty cool. But if I tell you, I have to kill you.
It's tough because the problem is in SLAM nowadays, is LiDAR systems are generating millions and millions of points.
No, but the majority of those are photography. We don't create a lot of LiDAR points, it's just correction points.
Yeah, that's right. Okay. So the big issue is like figuring out the important ones, right? And so, SLAM, one of the constant issues is what information do you throw away when you perform SLAM? And that's
their algorithm.
I think they're still.
And they are doing replacement of real models to make the models faster. They replace the real tree by a model tree.
Yeah.
They are replacing everything for artificial representation. I have some pictures, but I'm not allowed to show them.
I have a question.
Yes.
I know that you are an excellent researcher, but also a great educator. And in our audience, we have a good mixture of undergrad and grad students, mostly from the civil engineering. And there is a growing importance and an interest about the data science. So how civil engineering students can prepare for that kind of new study?
I think that it's fundamental. It's not how. It's the question that if they don't, the others, it's the example that I used from the bridge. It's much easier for you that understand the behavior of the bridge to define where the sensors and do the analysis, to get a computer science and to teach them about the structural behavior. Okay? So all those things that are being developed by civil engineers with the help from those guys, but cannot be the leadership from them, because the domain is much more important to understand the domain than to understand the technology. So, and this is not rocket science. So we do teach. And the first thing that I do is to show the students how dumb a neural network is. Okay? It's a stupid brute force. And people, oh, neural networks. I can teach neural networks in 20 minutes. Okay? And I cannot teach structural behavior in 20 minutes. So we are teaching those things, but the first thing that you do a very introduction class to make sure that the students don't have that, oh my God, artificial intelligence, this is computer, it's everything, there is no intelligence in artificial intelligence. Artificial intelligence is as dumb as hell. Okay? So it's 90% of those algorithms is brute force. Okay? It goes use the computer capability of looking at the data over and over and over again to find a pattern. And those things are extremely stupid. And people say that neural network, it's mimicking the brain. If my brain works like a neural network, I will kill myself. Okay? Because that is pretty stupid. So the idea is we have, and we are teaching. Carnegie Mellon teaches, USC is teaching, Stanford is teaching, so the students are taking, and it's not even an optional class, it's a required class. So, and it's so easy for the students to learn, because they are not difficult. Yeah, there are some requirements in programming in some of the tools, but again, it's so many programming, and we can teach, for example, in my class I teach LabVIEW. Okay, the students have to know how to get a sensor, get the data from a sensor to a computer. So that's this. Yeah, they learn. There's no problem. But it's always good to have basic knowledge in programming, knowing C++, and those things that give you the. Not that LabVIEW has anything to do with C++, but understanding the rationale of algorithms and flowcharts and how things work. Python. You have to go to those things, but those are very, very easy. I never had a class on all those things. I never had a C++ class, and I taught C++ at MIT. You get books, you learn those things. I cannot imagine me getting a book and learning structural engineering myself. I had a lot of help to learn those things. But everything computing when I went to got books and learned.
I think we can take one more question if you have. If not, then let's thank Dr. Soibelman. And this is the last seminar in this year, so then we will start from January. So I will announce. Okay. So, thank you.